Hello, this is Nick Andre welcoming you to the screencast, Application Layer Functionality and Protocols, Chapter 3 of Network Fundamentals. In this screencast, we will study the first three layers of the OSI model and learn how it provides network services to end-user applications. Explore application protocols such as the World Wide Web and their related services. Wrapping the screencast up will be a packet tracer demonstration examining and explaining how common user applications work. On another screencast, I discussed what the OSI model was and what it meant to a network administrator. In short, OSI stands for Open System of Interconnection. This model helps us understand the communication process a lot better by illustrating what layer protocols will do to data as it passes from layer to layer. In this screencast, we will be focusing our attention on the first three layers of this model: application, presentation, and session. More importantly, on the protocols that operate on either model's application layer, such as DNS, Domain Name Services, used to resolve internet names to IP addresses; HTTP, Hypertext Transfer Protocol, designed to carry web pages around the web; SMTP, Simple Mail Transfer Protocol, which delivers emails and attachments to servers; and its sister protocol, POP, aka Post Office Protocol, used to deliver emails to clients. Layer 7, the application layer, provides the interface between the applications you use to communicate with and the underlying network over which your messages are transmitted. In other words, people, also known as clients, initiate data exchanges. That is to say, they communicate by using software. Using the OSI model, let's see how this process works. Applications interface people with hardware. Hardware converts the message into a digital format. This occurs at layer 6. Layer 5 initiates the data transfer by creating a dialogue between the source and destination application. This dialogue becomes known as a session. After the session is established, the OSI layers encapsulate data down the stack. The encapsulated data travels across the networks until it arrives at its final destination. This end device will strip the encapsulation data, add it to the message by the sender as it is passed up the stack. The original message is passed to the requested service for processing. There are two forms of application layer software: applications and services. Applications are used by clients that require a network connection. They understand the OSI model and produce data that is ready for encapsulation. Examples of client-side software would be a web browser. Services are applications installed on a server that run in the background, listen for requests made by the client. Sometimes they are known as daemons and/or processes. In either case, they help to complete the communication process by offering a means to share resources. Example of server-side software would be a Hypertext Transfer Protocol daemon or Internet Information Service. A web browser, in short, retrieves web pages from a web server using HTTP, an application layer protocol. The client initiates this conversation using an application, and a server completes this process by using a service. In this example, the web server must have the HTTPD service running in order for the server to fulfill the client's request. Most, if not all, application layer protocols will require the client and server to have matching counter protocols, i.e. HTTP and HTTPD. This relationship helps to activate correct services when messages are being passed. They also establish the message format so each end device can understand each other. Like specialized software, application layer protocols are unique to the application's purpose. This is not to say that an application can only support one protocol, but rather a protocol serves a single purpose and an application can support multiple protocols. For example, a web browser supporting not only HTTP, but also the secure side of HTTPS. The client-server model is the core of any dialogue. Even peer-to-peer networks can be represented by the client-server model. In both models, clients are the ones who initiate the data exchange, or start the communication process, if you will. And in both models, clients can upload data to a server if they choose to. The only difference is in implementation and in administration. In the client-server model, administration is centralized, making it easier to enforce security and implement change. Since files are stored in a central location, archiving becomes easier. All of this isn't without a price. In fact, this type of implementation requires expensive, dedicated hardware to serve the needs of clients. One example of dedicated hardware would be a server. A server is like a warehouse. It spends most of its time fulfilling orders. However, not all data travels down from the server. Most content today is provided by clients. As a result, servers receive data as well as send data. When a client receives data from a server, the client is said to be downloading. When the server receives data from the client is said to be uploading. Remember, the client initiates the conversation. A server can choose to entertain this conversation if the complement service is running and or if the client has permission. Typically, a server will have a public side, a side which anybody can access, and a private side. The client uploads through the private side and decides whether or not to make the resource public. Servers usually process multiple client requests at the same time. To distinguish between these connections and their respective service, a server has to depend on lower layers like the session and transport layers. The transport layer will identify which service is being requested. The service layer will identify the user making the request. A peer-to-peer network can be considered as being an uncommitted client-server network. Resources on a peer-to-peer network are not stored in a central location. Rather, they are stored on each peer and are shared without a dedicated server. Any peer that responds to a file sharing request is functioning as a server, and the client would be the peer asking for the resource. A peer-to-peer application is not to be confused with a peer-to-peer network. A peer-to-peer network refers to the physical implementation of a network. In the previous example, I had two computers directly connected to each other sharing a printer. Although a peer-to-peer network can be larger, they all lack a dedicated server. One peer becomes the server for one particular client during that conversation. Roles may change as new dialogues are formed. A peer-to-peer application refers to the logical implementation of a network. That is to say, a peer-to-peer application. Each peer can act as both a client and a server within the same communication and can exist on a client-server network. A dedicated server like Pirate Bay and torrent software would be an example of this. Pirate Bay contains a centralized directory of files and a list of peers that contain those files. These peers are commonly referred to as being seeders. Anyone using an application that understands the NetTilla protocol can trade resources with each other as long as each peer has their application running. Peer-to-peer applications are very flexible. Unlike peer-to-peer networks, peer-to-peer applications can have more than one peer act as a server to fulfill the request of a single client. As a result, security is difficult to enforce. Just ask the RIAA. Since multiple copies of the same resources are distributed across the internet, shutting down one peer will not bring the whole organization down. Other common protocols of the application layer and their respective port addresses are listed in this table. A few of them you have heard from me already, like DNS being the phone book of the internet and HTTP as being the web protocol. We will be exploring these protocols and others on later slides. For now, I'd like to bring your attention to the Telnet protocol. Telnet provides a virtual connection for remote access. You can think of this as being the DOS equivalent of remote desktop. We will be using this program as the semester progresses. Application layer protocols help to define the message that is passed from client to server. Whether the client is accessing a secure website using HTTPS or an insecure site using HTTP, both protocols define the three basic types of a hypertext message: GET, POST, and PUT. This message type helps the server decide what to do with the data. Another popular service used by all of us without knowing it is domain name services. In a nutshell, DNS takes a domain name like www.google.com and uses a resource record to resolve the name into an IP address. This is why so many people call it the phone book of the Internet. Out of all the services we will discuss, this is one of the few protocols that do not have a counter protocol. The client and server both use a DNS resolver to look up an address. This resolver is commonly known as named. That is the word name followed by the letter D to indicate that it is a daemon. Because of its hierarchical nature, both clients and servers will use this resolver. When a client makes a query, the named process first checks their own records. If unable to resolve it, the server will become a client and contact other servers to resolve the name. Requests can be passed up the DNS ladder until a match is found or the top is reached, all the while taking extra time and consuming more bandwidth. Each time the request arrives at a DNS server, the named process checks to see if they can find a match. If a match is found, it is passed down the ladder, updating, that is caching, as it works its way down. Once it reaches the client will cache the results to prevent future lookups. The command nslookup can be used to manually or force query your DNS server, just in case your DNS cache is out of date. Most of the time, this service is automated. Before using the nslookup command, you might want to see what is stored in your cache. The command to display the DNS cache is as follows: ipconfig /display DNS. Email used to be static, like snail mail. In order to send or receive an email, you must be on a computer that contains an email application that understood two basic protocols: POP for downloading email and SMTP for sending email. Your authentication information was also stored. As a result, people would access their email from their personal computer at home. As you well know, that is not the case today. A user sends or receives email from the client's mail user agent, such as Outlook, web browser, phone, etc. Any email that is sent from an MUA is first sent to the user's email server using SMTP. The email server will check to see if the recipient has an inbox on the server. If the recipient has an inbox on the server, the mail transfer agent, MTA for short, will deliver it to the MDA, or mail delivery agent, where it will wait until the MUA asks for a new message, at which point the MDA, using POP, will deliver the message to the MUA's inbox. What if the recipient doesn't share the same email server? Once the email server realizes that the recipient is not on its list of users, it will use a mail transfer agent to send the email to another server. The MTA will deliver this email using Simple Mail Transfer Protocol, SMTP, to the next email server. This email server will repeat the process. Check if the user is on its list. If so, use an MTA to deliver it to an MDA. If not, use the MTA with SMTP and pass it on to the next email server. This process will go on until so many servers were tried, or until the message ends up in an MDA waiting for the client to retrieve it. Another protocol that has been integrated into modern web applications is FTP. FTP is short for File Transfer Protocol. It is commonly used to transfer files between clients and servers. You use FTP when you are attaching a packet tracer assignment to Blackboard. Notice that FTP uses two port addresses, one for control information and the other for data. You'll be asked in future assignments to know these addresses. Speaking of file sharing protocols, SMB, Server Message Block, is extremely popular amongst Windows users. If you have ever right-clicked on a file and chose Share this file, then you have used SMB. The same goes for sharing a printer on your network. Like DNS, DHCP is another service that is automated and goes unnoticed. As the name suggests, a DHCP server dynamically assigns IP addresses to host computers on a local area network. I will demonstrate this technology on another packet tracer screencast. For most, DHCP servers come pre-installed on wireless routers and are integrated service routers provided to us by our ISPs. In an earlier slide, I brought your attention to a service known as Telnet. I told you that it was like the DOS equivalent to remote desktop. That is to say, it is a means to remotely access systems by creating virtual terminal sessions. Terminal is a reference to the old mainframe days in which an organization had a large server and users would access computer resources from remote terminals throughout the organization. Most of the time these terminals were local to the organization and therefore security wasn't a concern. This isn't the case today. Since Telnet does not support encryption, many network administrators use SSH, which is short for Secure Shell, which, like Telnet, allows for remote sessions, but the sessions are encrypted. Let's put it all together. When a user boots up their computer, the DHCP service will kick in to assign the computer an address. Remember the four elements of a network: two or more end devices connected together by a medium to share resources governed by a set of rules. In essence, the DHCP makes sure everyone on the network is using the same addressing rules. After the operating system loads, the user opens a web browser, thereby using HTTP to make a web request. Since the Internet Protocol only understands numerical addressing, the web browser must make a DNS request to resolve the domain into a IP address. The HTTP request will resume once the DNS service has resolved the name. When it resumes, it will send the web server, using an IP address instead of the domain, a request. A daemon on the server responds to the request and a session is created. Upon receiving the web page from the server, the presentation layer converts the data back into information for the user to understand. Next, the user clicks on the inbox link to check for any new mail. Now the web browser will act as a mail user agent and check the mail delivery agent for any new emails. If any new emails exist, the MDA, using the post office protocol, will deliver the email back to the web browser. In this final example, we can see that the application protocols can work together to accomplish the purpose of networking, and that is to share resources. This concludes Chapter 3, Application Layer Functionality and Protocols screencast. We explored the application layer of the OSI model and had a bowl full of network alphabet soup. To summarize and simplify this chapter, apps call, daemons respond, and protocols regulate. See you in the next screencast. Take care.